Okay, good afternoon, professors. Welcome to my candidacy exam. So here's the outline of my presentation today. First of all, we'll introduce some preliminary notions, including first, the matrix Diophantine approximation, which generalizes the Diophantine approximation in one-dimensional case. To connect this notion to the dynamical systems, we shall introduce the Dani's correspondence principle. Which is introduced by Dani in 1985. And thirdly, to measure the points of Diophantine approximation in RD with certain properties, we introduce the Hausdorff and Parkin dimensions, which basically measures the size of the set of certain points. In the second part, we'll introduce the variational principle. The variational principle is an important tool introduced recently by Das, Fishman, Simons, and Urbanski in their very, very long paper called a variational principle in the parametric geometry of numbers. So this section will be pretty technical. So in the first two subsections, we'll introduce lots of notations. And the variational principle is expressed in terms of those notations. The dimensional games, namely the topological games introduced by Wolfgang Schmidt, is the most important tool used in the proof of the variational principle. So in the third section, we'll talk about the applications of the variational principles. The most important application of the variational principle is that those mathematicians give the precise computation of the Hausdorff and Parkin dimension of the certain points. And other applications include the reproof of some old conjectures. The first section, I'm going to talk about some directions to further research. There will be some interesting problems. And the last section, we'll talk about some related topics. It's still about the Hausdorff dimension, but this time it will be more on the homogeneous dynamics side. Okay, so let's get started. First of all, we introduce the notion of called singular matrices. We can consider all n by n matrices with real entries. So a matrix is called singular if for all epsilon greater than 0, there exists a positive number q sub e such that for all q greater or equal to qe, there exists integer vectors, m-dimensional integer vectors p and n-dimensional integer vectors q, such that aq plus p, the norm of aq plus p, bounded by epsilon times the reciprocal of some certain power of q. So the set of the singular n by n matrices is denoted SING m comma n. And the second notion is called the badly approximable matrix. The singular matrix is something that we have a good approximation, namely the norm is bounded by some number, some small number from above. And the matrix that is badly approximable, the norm is the one in which the norm of AQ plus P is bounded below by some number. So this number cannot be too small. So there's a lower bound for this quantity in terms of some power of the reciprocal of the norm of Q. And the collections of badly approximable M by N matrices is denoted by BAMN. The third notion is called very well approximable matrices. This means there exists an epsilon greater than 0 and infinitely many integers P and Q such that this quantity is bounded by some small number. And the collection is denoted by VWA of M comma N. And as you can see from this definition that we have the very well approximable matrices is contained in the set of the singular matrices. And it is impossible that a matrix is both badly approximable and singular at the same time. So here's a quick example. So how this generalizes the situation in R1. So in the R1 setting, being singular is the same as being rational. This is the definition for singular matrices. In the R1 case, when M and N are both equal to 1, this is just epsilon over Q. And being singular will be same as being rational. And because if A is irrational, you cannot make epsilon very, very small. The best possible small epsilon is 1 over square root of 5, I think, which is a theorem of Hurewicz. And by Lewis' theorem, any quadratic irrational is badly approximable. But it seems to be still an open question whether other kind of irrational numbers are badly approximable. So we have introduced those three notions. Now we will look at how they correspond to the Dani's correspondence principle in the dynamics settings. So to introduce Dani's correspondence principle, we need to first introduce two types of matrices. The first one is a diagonal matrix with positive and negative power of exponentials. The second one is the upper triangular matrix with A placed in the upper right of the matrix. So let x naught equal to Zn as an element of the quotient space Rn mod Zn. So the following table gives the correspondence introduced by Dani in 1985. So if A is badly approximable, then the orbit of x naught under the action of GTUA is bounded. And A singular corresponds to A being singular corresponds to this orbit being divergent. A being very well approximable corresponding to the limb soup of the distance between x naught and the GTU x naught divided by t is greater than 0. This means that the orbit is not only divergent, but also divergent at least linearly. So when it is divided by t and you take the limb soup, you still get the positive number when t is large. It can be shown that those three type of matrices of measure 0 In order to give the size of those matrices a more precise description, further need to discuss the Hausdorff unpacking dimension of those matrices. First of all, let us briefly recall the definition of the Hausdorff unpacking dimensions. The Hausdorff dimension is defined through the Hausdorff measure. The S-dimensional Hausdorff measure is a set where you take the limb sup of the summation of the S power of the diameter of UIs whose union covers S, and the diameter is less than delta. And the Hausdorff dimension of the set will be the infimum of D with this Hausdorff measure of S equal to 0. This also can be proved to be equal to the supremum of those D's with HD of S equal to infinity. And similarly, we have the notion of the S-dimensional packing dimension. We first define the S-dimensional packing measure. So to introduce the packing dimension, we first need to introduce the notion of a packing measure, which is the infimum of all possible summations of those terms with P naught S of Sj is called the S-dimension of the packing premeasure. I will introduce it below, satisfying that the S is contained in the countable union of those Sj's. And the P naught S, capital S, will be the limb sup of limb sup S delta goes to 0. Again, we'll consider the summation of the diameter of B sub i's raised to the S power, where B sub I is a complex collection of pairwise disjoint closed balls with diameter less than or equal to delta and centers in S. So this means we will put those balls with center in S and make sure they always disjoint with each other. And the packing dimension of a set is defined in a similar way as Hausdorff dimension. We take the infimum of those D's with PD of S equal to 0 and the supremum of those with PDS equal to infinity. But what is really used in the computing of the Hausdorff packing dimensions of those set of matrices is this theorem, this powerful theorem. And to introduce this theorem, and we need this definition. The mu be a Borel probability measure on RD, and we take a point from RD. There's a notion called lower and upper pointwise dimension with a measure at X, defined by taking the inf and limb sup, respectively, of the fraction, the logarithm of the Borel measure of the ball centered at X with radius R divided by log of R. So given this definition, we can simplify the computation of Hausdorff and packing dimensions by using this powerful theorem due to Rogers, Taylor, and Tricot, which states that if you know the information about the lower and upper pointwise dimensions, which are defined in somewhat simpler than the Hausdorff and Parkin dimensions. Then, if they are, they have a lower bound and upper bounds, and you can use this theorem to find the lower and upper bounds for the Hausdorff and Parkin dimensions. This is a really powerful theorem.